Last time we met, we were reviewing how to simplify radicals, right? We just did a lot of practice with that. And I gave you an assignment where you get lots of practice on that, okay? We ended up, as I recall, we didn't quite finish this guy up. So let's finish this one up, right? I've got this expression that involves a radical. Well, we got a good start on it. The suggestion was made, why don't we break this up? We've got a common denominator, so we could just split the fractions here, split this into two fractions instead of having a common denominator. And then we get 7/14 minus the square root of 98 over 14. And 7/14 reduces, doesn't it? Okay, so now what remains to be done here? What do we have to do here?
We have to do the 98 and, we could do the tree or whatever.
Okay, yeah, we got to simplify the square root, don't we? Okay, so we need to factor the 98, and we're going to go back and use our factor tree. And remember, our goal is we'd like to try to find some perfect square factors in this if we can. Okay, so help me out here. What can I do with the 98?
I took out a 2, and then it left me with the 49.
Okay, and 49 is good, isn't it? Because that's a perfect square, right? 49 is going to break up into a couple of 7s. And so we end up then with a couple of 7s and a single 2, right? So the square root of 98 then is going to become a 7 times the square root of 2, because couples go out and singles stay in, right? Divided by 14. Can I do anything with that?
You can simplify it, the 7 over 14 to 1/2, but then you take away the 1, so it's just going to be square root of 2 over 2.
There you go. Okay. So we can cancel like factors, right? Remember, I can vertically cancel like factors, and 7 is a factor of 14. So I'm going to think of the 14 as being a 2 times 7, and I'm canceling the 7, right? And so we end up then with our final answer just looks like 1/2 minus the 7 cancels top and bottom, so I'm just left with a square root of 2 over 2. There's our answer. Okay, everybody good? All right, so now it's time for us to go back. We've had enough practice with simplifying radicals that let's go back to that original question that I posed to you folks, this quadratic equation. We're trying to solve this thing. Adelaide, as I recall, had a good suggestion. Let's go ahead and add the 5 to both sides. And that was a good thing to do because it isolated the part that's being squared, right? This is consistent with the idea of reversing the order of operations to isolate that single x, right? If you can point to a single x, you can isolate it by reversing order of operations. Okay, so there was a subtraction step or an addition step of adding 5. There was no multiplication to do, but the next thing we came to was the exponent, right? And we started talking about that, but that's where we kind of got left off. How do we undo squaring that quantity 3x minus 4?
Square root.
Square root both sides, right? Yeah, I'm going to square root both sides. If I square root both sides here, think what that's going to do. So I'm going to take the square root of the quantity 3x minus 4 squared equals the square root of 81. And the whole point of doing that, right, is so we could cancel that squared, right? So what do we end up with for our answer? Okay, so we end up with a 3x minus 4 equals 9. Okay, And if we go further with that, we could add 4 and divide by 3, and we'd get what, 13/3 for our answer? Agreed? Okay, let's check that one graphically, and we might as well, I kind of want to start making connections between the function and its graph. So what if I go into Desmos here? Let's go into Desmos and graph this thing and see what we get. So here's our original equation, the quantity 3x minus 4 squared minus 5. Okay, so there's the function on the left. Okay, the function on the right is 76, right? So let's call this like y equals the left side. Remember how we can do this trick? We can do y equals the right side. And we're just looking for the points of intersection, right? So if I zoom out a whole bunch here, it looks like I've got 2 points of intersection. Well, there's one of them at x equal, there's 13/3, right? 4.333. Everybody agree? Okay, good. All right, that looks pretty good. Looks like we got it, huh? Except, hold on here. We missed one somehow, huh? Look at that. There's one, but there's another solution right there. It looks like negative 5/3. This should be another example. Well, how'd we miss that? What happened? You seem to do the right stuff. The square root of 81 is 9. And when I took the square root of the squared, it undid the squared. But hold on a second. Maybe there's more to it than that. Let's take a look at this here from a different perspective. Let's just see what happens if let's take a simpler version of a function. I'm just going to work kind of separately here.
Is it positive or negative 9?
It is. It's positive or negative 9. Okay. But how come? How come? Let's think about this. If I start off with a simpler version here, let's say we have something like just x squared equals 4, for example. If I square root both sides, I'm going to get the square root of x squared equals 2. Okay, what is the square root of x squared? Let's think about just that function for a second. Let's take the function f of x equals the square root of x squared. Let's just focus on that guy right there. Okay, so what happens here if I plug in like a 4? Let's calculate f of 4. That's the square root of 4 squared, which is the square root of 16, which is 4. Everybody agree? Or sorry, yeah, right? That's just going to give me back a 4, isn't it? If I plug a 4 in, right? So f of 4 gives me an output of 4 for this bizarre function right here. Okay, everybody agree? Maybe I don't want to use a 4. Let's use a 2 instead. Not that it really matters, but it might just help a little bit if we use a 2 here. So if I input a 2 into the function, the square root of x squared, I get the square root of 2 squared, which is the square root of 4, which is 2. Okay, what if we input a negative 2? What's the square root of the quantity of the number negative 2 squared? Well, what is negative 2 squared? Everybody? That's 4, isn't it? Square root of 4, so I get a 2. Well, hold it now. If I input a 2, it outputs a 2. If I input a negative 2, it outputs a 2. What if I just input an a and a negative a? Let's just try that. I input an a, I get the square root of a squared, which is a. If I input any negative number, call it negative a, I get the square root of the quantity negative a squared, which is the same thing as the square root of -1 squared times a squared. That's the square root of a squared, which is a. Now, what function do we know that behaves like that? If I plug in a positive, it leaves it alone, but if I plug in a negative, it makes it its opposite positive. What function do we know that behaves exactly like that? Absolute value, yeah. Okay, so by definition, the function, the square root of x squared, is equal to the absolute value of x. And so here's a missing step that is really never taught in algebra classes. There is a missing step here. When I square root both sides of this equation, what I actually end up with here is the absolute value of 3x minus 4 equals 9. Going back to our discussion of solving absolute value equations, what did we do? If we had an absolute value expression equal to a number, didn't we just set whatever was inside equal to plus or minus the number that was outside? Wasn't that our strategy? Right? Everybody get that? Okay, so we know we don't have to show that step. That's kind of an invisible step. We don't need to show it every time. But we do know that if I'm solving an equation and I square root both sides to undo a squared, I always have to include a plus or minus in my answer because of that missing step there. Okay? So this is what we refer to in math as the square root property. Okay, when solving a quadratic function where you can point to a single variable, you can isolate the variable by using inverse operations, which we did. However, when you square root both sides, you have to include both the positive and the negative square root. Okay, always. So let's get a little practice with this then. Let's just start easy and we'll work into some harder ones. So let's solve this quadratic equation. Okay, we can solve this one using the square root property here because anytime we can point to a single x and it's a quadratic function, this is the easiest way to solve it. Just like factoring was easiest when we had a trinomial and we could find magic numbers easily, right? In this case, where I can point to a single x and it's quadratic, we always want to just isolate the x by reversing order of operations, okay? So what are we going to do first on this one? Everybody agree if I'm reversing order of operations here, I'm just going to subtract 44 first. Everybody good with that? Give me a thumbs up. Does that make sense? Okay, so then that's going to give us 4x squared equals 3, what is that going to be? 398? No, what am I doing here? What is that? Help me out here. Gosh, why am I having a brain fart here? What's going on? 44. Oh, 392. There we go, right? Yeah, I did that right. Whew, why was that so hard? I don't know. It must be Friday, huh? So now what? Now what do I do? Just type it in chat or say it, somebody. What do I do next to solve?
Square root of both sides.
Yeah. Okay, good. So say it again. Say it again, Ray.
You take the square root of both sides.
Not yet. Not yet. We're not there yet, right? We gotta reverse the order of operations.
Oh, so we divide 4.
There you go. Okay, good. So first we added or subtracted. Now we're going to divide each side by 4. Okay, and so we end up with x squared equals, what's that going to be? 98. Okay, now finally we're up to exponents. And so now we can square root both sides, right? Okay, if I square root both sides, remember what that's going to do. So it undoes the squared. I end up with x equals, and now I've got to simplify the square root of 98. Well, we already did that one, right? That's just 2 times 49, and 49 is 7 squared. So we know we're going to get a 7 radical 2, but I have to include that plus or minus, right? Because I square rooted both sides to solve an equation. So I have to include that plus or minus. Everybody get that? So I get two solutions out of this. Positive 7 radical 2 or negative 7 radical 2. Okay? But give me a 1 to 5 on that. Does that make sense? Okay? All right, let's do another one. How about this guy? Well, I'm just going to reverse order of operations again, right? And how come? Because I can point to a single x. Does everybody agree that this is quadratic? If I were to expand this whole thing out, I could. Everybody see that I could put this in the form ax squared plus bx plus c equals 0. We're not going to do that. Does everybody agree that I could do that if I really wanted to? Right? So it is quadratic. It's a quadratic equation, and I can point to a single x. So our strategy is reverse order of operations and isolate x. So first we've got addition or subtraction. Yeah, you bet. We're going to add 5. This is outside of the parentheses, right? We have parentheses in this one. So we're going to add 5 to both sides. That's going to give us the quantity 3x minus 4 squared equals 81. What's next? Just type it in chat, everybody. What's next? What do I do next? Should get answers from everybody on this. Want to make sure everybody's with me and getting this. What do we do next? Okay, good. We square root. There's no multiplication or division, but we do have to undo that exponent, right? So I square root both sides, and I get 3x minus 4 equals, well, the square root of 81 is 9. What do I have to include here? Positive and negative. So 3x plus 4 equals plus or minus 9. Okay, now what? Okay, now finally I move up and I've got this parentheses step, right? I used to have these parentheses here. I don't really need them anymore, do I? Because nothing is being distributed now and it's not being taken to a power. So we can get rid of the parentheses, but I still have to isolate the x. Well, what are the 2 steps in order to isolate that x? Carrie, what are my 2 steps in order to isolate that x? Good. Add 4, divide by 3. Okay. Now, here's a trick, though. When I do those 2 steps, because I've got 2 solutions coming out of this eventually, one for the positive and one for the negative 9, right? Here's a really good trick. I'm going to, when I add that 4, I'm always going to put it in front of the plus or minus, right? So I'm going to get 3x equals 4 plus or minus 9. And then the last step is, remember, is just we're going to divide by 3. Well, there's both of my answers, right? Everybody see that? So I end up with x. If I take the plus sign, I'm going to get x equals 4 plus 9, which is 13/3. If I take the minus sign, I'm going to get x equals 4 minus 9, which is negative 5/3. Everybody see that? That's a good way to sort of compact the math there. Just always add in front of the plus or minus sign. Then you get both answers at once. You see that the alternative would just be more writing. Okay? Okay, how about this guy? A little bigger one, right? But it doesn't matter. It doesn't matter how big they are. We know what the recipe is. We're just going to reverse order of operations. Once again, if I expanded this whole thing out, it would be a quadratic equation in standard form. So it is quadratic, and I can point to a single x. So I know I'm just reversing order of operations to isolate that x, right? Okay, so first step, everybody type it in chat. What am I doing first here? Good, subtract 10. Okay, so first step then is going to put us at negative 2 times the quantity 2x plus 3 squared equals negative 196. What's next? Type it in chat. Good. Divide by negative 2. So we end up with 2x plus 3 quantity squared equals positive. Man, we're getting that 98 a lot, aren't we? Positive 98. Now what? Everybody type it in chat. I'm not hearing from everybody. Let me hear from everybody here. Okay, good. So we're square rooting. Good. Square root both sides. So that's going to give me 2x plus 3 equals, we've already done the square root of 98 a couple times, right? That breaks into 49 and 2. Square root of 49 is 7. Okay. Is that good? Oh, good. That plus or minus. All right. Everybody's remembering. Okay, now what's next? Okay, subtract 3. Now, where am I going to put the negative 3? Rebecca, where do I put that negative 3 when I subtract 3? Yeah, good. In front of the plus or minus. Good. There we go. So it's going, we can do this, can't we? We can subtract the 3 and put it there. And then finally, last step, everybody all at once in chorus here. Beautiful mathematical chorus. What's our last step? That's not much of a beautiful mathematical chorus. Oh, you're not going to see. You guys just writing it in chat. I was hoping you'd all just chime in on your mics and all say it at the same time. That's all right, though. We divide everything by 2, don't we? Okay. Good. Okay, we divide everything by 2. And then what do we end up with when we do that? Well, we can split this fraction. So we could leave it like that, but really it's better because we have a plus or minus here. Let's just do this. Negative 3 halves plus or minus, and then there's nothing I can do to simplify the other fraction, right? I just end up with 7 times the square root of 2 over 2. There's both my answers in one. Plus or minus. Okay, make sense? Okay. More of the same here. Okay, let's maybe we'll speed through this one. This is getting a little bit old now. You guys, I'm sure, are getting all this down, but there's an important step I want to address in this process. So everybody agrees this time, I'm sure that we're going to start off by subtracting 9. So we get negative 2 times the quantity, negative 5x minus 3 squared equals negative 112. Now we're going to divide by negative 2, right? And we get the quantity negative 5x minus 3 squared equals positive 56. Now we're going to square root both sides, right? And we got to deal with the square root of 56. Well, let's make our factor tree. What can I break out from that 56? Okay, I could do a 7 and an 8. Good. Good. We'll chunk it a little bit, and then the 8's a 2 times a 4, and the 4 gives me a couple of 2's, right? So we end up with a couple of 2's and a different color, single 7 and a single 2, right? So then this is going to end up giving us, on the other side of this equation, I have to include my plus or minus, right? Because I square rooted both sides. My 56 breaks up into 2 times the square root of 7 times 2, which is 14. Give me a thumbs up. Everybody good with that? Okay, good. And we undid the squared with our square root, and so we get a negative 5x minus 3. Okay, let's see. Pagan, what's next?
Sorry, my mic wasn't on meeting. What was the question?
Well, that's okay. So what's next here? Gotta get.
You would add 3, right?
Okay, good. And where am I going to put the 3?
In front.
Perfect. In front of the plus or minus. So we could do this, right? We're going to put the 3 there. And now here's the weird part, right? We're dividing by a negative 5. I'm going to rewrite this because I want to focus on this last step. So we're left with negative 5x equals 3 plus or minus 2 times the square root of 14. Well, the natural thing is to divide by negative 5. Everybody agree? Okay. So I'm going to divide everything by negative 5. Let's do 2 steps in one. Being as I'm dividing that whole thing by negative 5, couldn't I just split the 2 fractions and divide each one separately by negative 5? Does that make sense? Give me a thumbs up. Are we all good on that? Okay. So I end up with, when I divide by negative 5, I'm dividing the first term by negative 5 and the second term by negative 5. But does that make sense? Isn't that making things excessively complicated on that second one? Because look, we already have a plus or a minus there, right? I have plus or minus that quotient, 2 radical 14 divided by negative 5. Well, what's the point of dividing by a negative number if I'm already including both signs? Everybody agree with me? Okay, so you see the moral of the story here is when you're faced with a situation like this, it's not like this is such a profound thing, but it makes the math a little bit easier. Whenever I'm dealing with a situation where I have a plus or minus term, a positive and a negative term, I never divide by a negative. There's no point. I might as well just make that a positive 5 on the bottom, right? What's the point of adding and subtracting a negative? It's the same thing as adding or subtracting the same opposite positive, isn't it? Okay, so then I always just say you divide by an absolute value if you have a plus or minus term. Okay, so then we end up with our final answer just looks like x equals negative 3/5 plus or minus 2 radical 14 over 5. Okay, everybody see that? Okay, so what about this one? What if, just slightly different terminology, what if this asks me to find all the x-intercepts? We don't even have to necessarily do the whole problem. I just want to know, how would we set this up as a problem that we could solve? Where do the x-intercepts of a function always occur? Say that again, Maria.
I wrote it in the chat that x-intercepts are solutions, but now I'm second guessing myself.
No, they are. X-intercepts are solutions. You're right. But if I look at on any function, let's just do a quick graph of a random function for a second. Whoops. There we go. So if I've got just some random function f, right? The x-intercept always occurs at the point where the y value is 0, doesn't it? Always, right? because an x-intercept by definition is on the x-axis, and on the x-axis, the y-coordinate is always 0, right? Well, the y-coordinate is just the output of the function. Everybody see that? So when we're asking for x-intercepts, what we're really just asking about is where does the function equal 0? So we oftentimes say x-intercepts are the same thing as zeros, right? How come there's zeros? Well, it's because it's where the function is 0. So the moral of the story here, and this is something we're going to do a lot in the future, when we're looking for x-intercepts, well, we're just setting the function equal to 0 and solving. And now we have a simple quadratic equation that we could easily solve. Everybody agree? And we don't even have to do it. We've done enough of those, right? But we could solve that. Okay, give me thumbs up on that. Are we good? Thumbs up, thumbs down, thumbs sideways. Does that make sense? Okay. Okay, what about this one? Oh, you know what I forgot to do here? I forgot to, let me check something. I think what I meant to do on this, I'm sure, yeah, I don't have to even look. I know what I meant to do on this is I meant to have an exponent there. Okay. 2. Solve for x. Okay. Assume that the constants a, b, c, d, and e have values for which the equation has exactly 2 real number solutions. So we're going to assume that we get 2 solutions out of this. Okay, this is strange, right? Because those aren't numbers, but who cares, right? If I'm solving for x, solving means isolating. Everybody agree? So even though those constants are not written as real numbers that I can easily combine and simplify, I still treat this algebraically the same as I did all those previous examples. Okay? When I end up isolating the x, are we going to be surprised if in our answers we see some a's and b's and c's and d's and e's? No, right? We would expect that those things would be there, right? But we're still going to get solutions that are going to be valid solutions in terms of whatever those values are, A, B, C, D, and E. Those are what we call parameters. We treat those as though they're constants, but then we can always go back and say, okay, well, what if we tweak the values of those parameters? We could let A, B, C, D, and E be any constant numbers that we choose, right? We still can solve for the variable x in terms of those parameters. Okay, so the parameters almost feel like variables a little bit because we could tweak their values, but they're not. Within the context of this equation, we're assuming that those are all constants and this is the variable that we're going to isolate. So you guys tell me then, this is going to be a weird one, but tell me, what are the steps I'm going to go through to isolate that x? What's first? Type it in chat. Okay, subtract d. There we go. So first we're just reversing order of operations just like we always do. So first we're going to subtract d and get the quantity, or a times the quantity bx minus c squared equals e minus d. What's next? Good. Divide by a. Okay, we divide each side through by a, and we get that. Okay, so now we have the quantity bx minus c squared equals e minus d over a. Now what? Square root. Okay, good. Square root both sides, which means I have to include a plus or minus, right? And I'm just going to get the square root of that whole thing, which I could break up into the square root of e minus d over the square root of a. And over here, I just get a bx minus c. And what do I already included the plus or minus, right? We already got the plus or minus there. Okay, but there's something we can do here. Something doesn't look quite right about that. What's wrong with our the expression on the right there?
It has a square root in the denominator.
Yeah, no tenths in the basement, right? We got to rationalize that denominator. So how do we do that? What am I going to multiply top and bottom by?
The square root of a.
Square root of a. There we go. Okay, so then this is going to give us plus or minus the square root of a times the square root of e minus d. If I want to, I can just make that look like that too, couldn't I, right? I could combine those into one big square root if I want to, divided by a. Okay, and then the last few steps in order, what are those going to be? Okay, so I'm adding c, I see. Good. See in the chat there. So we're going to add c, and that's going to be in front of the plus or minus, right? And then finally, last step would be divide by b, correct? Okay, dividing by b, though, is that's a little bit awkward to divide that whole thing by b. Dividing by b is the same as multiplying by what? Okay, I'm seeing some people signing very effectively, 1 divided by b. That was good, House. I like that. So why don't we, in this case, does everybody see that it would be a little bit more convenient here maybe to multiply both sides by 1 over b? I'll just distribute that through. And if I distribute the 1 over b through, I'm going to get x equals, when I distribute to this term, I'm just going to get c over b plus or minus. When I distribute to this term, I'm going to get the square root of a times the quantity e minus d. And I could make those separate square roots if I wanted to. It's no big deal. Divided by a times b. So those are my two answers. Everybody agree? Okay. We got it. All right. What else did I have in store? Oh, you know what? I think I'm going to stop here. I don't want to go any further with this stuff. I think that's enough for you guys. That's enough for one day. I'm going to let you have an opportunity here to just kind of practice this a little bit. Why don't you get started on the assignment? Which one is this? This is assignment. I know I put it in the title here. Oh, no, I didn't. Is this 3.3 practice or 4.3 practice 2 maybe? I'll look and see. I'm pretty sure that's it. Is that it? Okay. You can, yeah, exactly. You guys could, if you want to go out and go sledding for 10 minutes, I'm okay with that too. It's how often do we get 10 inches of snow in Pendleton? So I'll give you the last few minutes here. I'll be here. I'll stick around. If you have questions, you can work here. But if you want to go out and mess around in the snow for a few minutes, go for it. But I'll be here if you have any questions. And yes, Maria, it does look similar to the quadratic equation. And we are going to derive the quadratic formula, you mean. We're going to derive the quadratic formula very soon. You guys will actually get to build it from scratch, which is kind of a fun thing to do in math.